So with that said, I would like to go ahead and introduce our speaker for today. We are continuing on the theme of subseasonal to seasonal prediction and predictability with a talk by Victor Gensini. Victor is an associate professor in the Department of Geographic and Atmospheric Sciences at Northern Illinois University and guest faculty researcher at Argonne National Laboratory. His research interests include extreme weather and climate variability and change, with a recent publication in Nature Climate Change on reduced frequency and size of late 21st century snowstorms over North America. We're very happy to have Victor as a new PPAI panel member and are looking forward to his talk. Victor, please go ahead.
Jenny, thank you so much. And I'm actually going to start with a little research personal collage. Sometimes we do these webinars, right? It can be very impersonal, and I really miss the in-person interaction that conferences bring. And unfortunately, in the environment of COVID-19, we certainly don't see that opportunity continuing. And with our summer meeting coming up for the Clivar PPAI, we're going to do our best to facilitate, very productive virtual interaction. So if you see anything up here that interests you, you'll have to contact me offline. But I do a lot of field work, and I'm very interested in, as Jenny mentioned, extreme weather, and right now specifically subseasonal to seasonal variability and predictability. I'm also a major weather geek at heart, and for those of you on the line that know me, I love everything about weather analysis and forecasting, and I also teach some introductory and mid-level, intermediate level, as well as some upper level atmospheric science courses at NIU. So that's a little bit about me, and I got interested in severe weather like many of us do, not all of us, but many of us, when a significant event impacted my hometown in 2004. So as Jenny mentioned, I do a lot with climate variability and severe convective storms. My dissertation was really focused on a glimpse into what might happen when we run initial conditions from climate models into essentially use dynamical downscaling to initialize high resolution convective allowing or convective permitting regional climate models to investigate extreme events. So, 99.9 percentile and above, things like severe convective storms, which in the US we defined as tornadoes, large hail, and damaging convective wind gusts. My talk today is really going to be focused on two talks condensed into one, but the first aspect is just going to really establish, what is our current predictability limit using dynamical models, and then what can we do about the limitation, as you'll see that those models present to us in terms of getting into the week 2, week 3, week 4 lead times for extreme weather events like severe convective storms. So the map you're looking at right now is, pretty infamous month, April 2011. The fill colors here represent the number of hours with a significant tornado parameter greater than 1, which is somewhat used as a forecast, but also usually a diagnostic parameter to really understand how favorable the background convective environment is for tornadic supercells. And if you just kind of look qualitatively, there's a very significant correlation to where the atmosphere produced tornadoes during April of 2011. So we certainly have very active years like April 2011, late May of 2019, which I'll talk a little bit about later. Then we also have some fairly quiet years. This is the same sort of temporal span. We're looking at April again, but now April of 2016, you see a lot fewer number of significant tornado parameter hours and much fewer tornado reports. So one of the major driving questions then, right, if we understand the variability potentially of what's possible in a month like April or May, are there any climate factors or climate drivers that perhaps are driving the variability from, say, high years to low years to even average years? So one of my major research questions right now is just what are the leading modes of climate variability that are impacting SCS? And another one that I focused on quite a bit, and others as well, some of whom are actually listening in on this talk, are whether or not climate change is having an impact at all. And if it's not, is there any theoretical potential for impact? I'm not going to get too much into the second question today, but I do want to talk a little about the leading modes of climate variability and where we currently stand in terms of dynamical prediction of the background convective environment, because the models that we use in the extended range are models like the European Ensemble or the CFS V2 or some of the sub-X models or the GFS Ensemble, for example, are not capable of simulating hazards at the convective scale. Instead, they are 20, 30, 40 kilometer horizontal grid spacing, and all we're doing at that point is basically predicting whether or not the precipitation is convective in nature and whether or not the background environment that the convection is forming in has the potential to be severe. So like many of you in the CLIVAR PPAI and other groups, a lot of my research right now uses high performance computing, modeling, reanalysis, hindcasts, and machine learning, which is a growing area. And I think the data science panel is also looking into the ability to harness machine learning. And some of our recent proposals, although they've been denied, and if you follow me on Twitter, you've had to deal with some of my whining lately in regards to funding opportunities. But we think that machine learning is a way that we're going to be able to bridge the gap between the dynamical prediction and some of the statistical methods that can help bridge the gap, if you will, between traditional weather forecasting and subseasonal forecasting, say 2 weeks to 2 months in advance. So first research question actually stemmed from some discussions in one of NOAA's springtime GEMS, which is the hazardous weather test bed. It's a collaboration between academia, operational forecasters, researchers, and model developers that really puts everybody in the same room for a week. And unfortunately, it was virtual this week, but we still got some great interaction. And the research question was fairly simple. It's just how well can the U.S. flagship weather model, which in this case is defined as the GFS ensemble, predict on a daily scale severe weather occurrence? And then, the major question then is obviously at what forecast lead time does this dynamical prediction system diminish to zero? Obviously through theory and talking about things like chaos theory, we would expect somewhere in the week 2 window for this skill and this forecast skill to diminish to zero. So this is a paper I published with Mike Tippett from Columbia, and it's in GRL. It came out last year, and I'd be happy to answer any additional questions if you have a chance to read the paper. So traditional severe weather forecasts, if you're not familiar, are issued by the Storm Prediction Center for the public, and well, they're primarily for emergency managers, but they create these nice categorical risks, which is something of like the the Homeland Security terror threat level, a value of 1 through 5. These are actually driven on the back end by probabilistic forecasts of severe convective storms. So in this case, what's the probability of having a severe weather event, large hail, damaging winds, again, a tornado within 25 miles of a point? These probabilities are then kind of, they fall out into these categorical representations. So, you've probably seen these before. If you haven't, they're available on the Storm Prediction Center website. And the forecasts are relatively simple. The forecaster just defines an area. They start marking, ideas spatially of where there's potential for risk, right? The dots are essentially connected and the risk is drawn. And the quantification here, again, is in terms of probability, is the probability of having one of these extreme events within 25 miles of a point. And a 2% value may seem very low, and it is, but on a scale of 100, obviously. But when you compare that to background climatology for any given day, that's actually it's very high. It's significantly higher than the background climatology would be, in many cases, orders of magnitude larger. So the Storm Prediction Center uses these probabilistic, and then it falls out to these scales of slight, marginal, slight, enhanced, moderate, and high. And for this paper, we looked at the first categorical slight risk for each hazard, tornado, and hail. So for tornado, that's going to be the 5% value, and I'll reference this a couple times. Hail, that's going to be the 15% value. So in other words, at what level of risk are we first going to alert the public that there's this sort of level 2, right, slight risk enhancement? And we did that. We didn't want to go to the enhanced or the moderates or the highs because our sample size gets greatly reduced. So there's some issues with that as well. These events, if you look in space and time or Poisson distribution, they don't happen that often. And it's very, very tough to deal with the severe weather database just in general. It's littered with a lot of issues that make it very challenging to just kind of, run some statistics and pull any sort of meaningful conclusions right off of the top. So here's how these forecasts can be verified. This has been the traditional way to do that in the past. So this is a tornado outlook for April 9th, 2015. And then here are the tornado reports that happened on that day during the valid period of the outlook. And that's great. We could subjectively look at this forecast and say, well, there's a clustering of tornadoes across north central Illinois. There seems to be a pretty large false alarm area in the 5% area, and then again in the 2. overall, how do you grade that forecast? Is it a, B plus, A minus? Qualitatively, that's difficult to do. And so here's another example. You can kind of see, outlook for tornadoes. And then again, that seems to be a pretty good forecast. Here's maybe one that has higher probabilities and then more tornadoes happening outside the risk. So again, that's sort of a way to qualitatively look at it. But we need a better way. And this way has actually been in the literature for quite a while. And Harold Brooks and Nathan Hitchens decided that this would be a way to do this. And I really like this. It's essentially a way to recreate what a forecast might have looked like if you have a priori knowledge of the event. And so the mode here, the idea is called practically perfect. It's essentially a hindcast where you have some tornado or extreme weather event. You go back and run a kernel density estimate on it with a Gaussian smoother. And depending on your grid sizes, you can basically replicate the categorical thresholds that the Storm Prediction Center is forecasting for. And again, this is a nice way to say, all right, if you have some uncertainty at the outlook scale, right? We can't pinpoint where a hail event or a tornado event is going to be the morning of an event, but we might have a regional area where we outlook for severe storms. Let's go ahead and kind of recreate that uncertainty using a Gaussian filter that corresponds tightly to the probabilities that we would be forecasting for. And so we have a paper on this that we just released in BAMS, which really takes Nathan and Harold's ideas and kind of creates an archive hindcast going back to 1979 of all these events. That sort of becomes our predict and data set, right? This is our target variable. We have all these hindcasts that we're trying to predict. So here's an example, right? Again, how do you do that? And then you can smooth it and say, all right, well, here's the forecast. Here's the events in the red dots. Let's go ahead and run that Gaussian kernel smoother and see how it replicates, right? So you could imagine you could then correspond areas to hits, misses, false alarms, correct nulls, fill in your 2x2 contingency table, and then run all of your forecast validation statistics off of that. And if you're interested, there is a real-time operational page which takes yesterday's reports and runs this smoother on it. But I think more interestingly, we have an entire hindcast archive that was published with the BAMS paper that's available on my website. I'd be happy to stratify that data for anybody interested or aggregate it in any way. So getting back here to the question, okay, going, how well can, what's our flagship weather? This is going to be the GFS ensemble, so 20 members plus the control, and we're predicting whether or not the slight risk threshold is met for both tornado and hail. So again, the 5% threshold for tornado is what we're going to be forecasting for, the 15% for hail, these first two categorical slight risks. Most of you are familiar, I'm sure, with the GFS ensemble, although we'll be getting an upgrade here coming up in September. August, some of the reforecast data is just coming online. I'm really excited about getting our hands on that, as it will go out, at least one of the runs per week will go out to 30 plus days. But we have global coverage here. We're not looking anywhere other than the US, but the most important piece here is that we're going to use environments as the predictor. Very similar to the outlook process. Forecasters now have convective allowing models, things like updraft helicity, composite reflectivity that's being forecast by the models. But in the day 1, day 2, and day 3 process, the forecaster is still using the background environment, trying to understand the background environment as the ability to sort of the upper end of what's possible on many forecast days. So our predictor then from the GFS ensemble is going to be the supercell composite parameter. And we're going to mask the supercell composite parameter if there is no convective precipitation. So in other words, if the GFS member does not predict convective precipitation in that grid box, then we are not going to count it as a forecast for severe. We're using the SCP. If you're familiar with the supercell composite parameter, it's basically a combination of instability, directional, lower level wind shear, and deep layer shear. And it gives you a pretty good an idea of what the environment is capable of in terms of supercells. So there's obviously some issues here. We're kind of forecasting for supercells. We're not really forecasting for the convective mode. Maybe that's most often observed in the southeastern United States, where we get a lot of damaging wind events. But this is what a spatial plot a supercell composite parameter might look like if you're looking at the GFS ensemble forecast 198 hours in advance. And you can see quite a bit of variability. Here we're focused on the central plains. We have values anywhere from maybe 0.25, 0 to 0.25, all the way up to one model here predicting supercell composite values in Texas between 4 and 7. So this is really going to be our predictor. It's going to drive our forecast. In order to set this up, we throw out the first 12 hours and the last 12 hours. That gives us 15 days of forecast to analyze. And we're going to match up the 12Z to 12Z perfect hindcast with the 12Z to 12Z prediction accumulated supercell composite parameter from the GFS ensemble. We did this in the paper for all of 2016 and 17. We came up with about just shy of 4,000 forecasts. We did this for tornado and then again for hail. No changes to the predictor. We kept supercell composite parameter as the predictor for both hail and tornado. So going back to that hindcast, this might be what something looks like. We're again only interested in that 5% threshold. So this would be basically our hind. Here's what happened, right? This is our hindcast. Here's maybe what the GFS predicted, and we're going to have this for right day 1, day 2, day 3. We're going to have this all the way out to day 15 lead time, and then of course you have your 2x2 contingency table statistics that you can accumulate from this type of forecast. So the hits, the misses, the false alarms, and the correct nulls. And since we have 21 different representations of this blue area, we essentially can create a probabilistic forecast, which allows us to create the Breyer skill score, which is really important. So we're using a very simple 2x2 contingency table. I think most of you have probably, if you've taken a forecast or read a little bit about forecast verification, right? This is very common. Your hits, your misses, your collect nulls, and your false alarms. So I'm going to skip through that. And one of the things that I really like to do, and this was suggested by Mike Tippett based on some work that Harold Brooks, Greg Carbon, Sam Lill, and others did in the Bulletin of the American Meteorological Society, was to use Chiclet charts as a visualization for the forecast. And so I want to give you just a quick example of what these Chiclet charts for forecast. And I'm a huge fan of these, especially for week 1, week 2, but even in the sub-seasonal realm for forecasting. Essentially, a forecast runs, let's see if I can annotate this with the pen here. A forecast essentially runs diagonal on these charts, and the verification date then becomes a vertical stacked column. And the color fills on top that you're looking at are essentially the area of the continental United States seeing a value of supercell composite greater than 2. This is for spring of 2016 with the date running across the x-axis here. This is average from all the members. And then below this chart, we have essentially the verification area of both slight risk thresholds for hail in green and tornado in red. So the idea here being, if there's a large area of the continental United States covered with this favorable environmental parameter, then we ought to see a fairly large corresponding area in both hail, perhaps, and tornado activities stacked on one another here. So if you just kind of take a step back and look at this, you can definitely see the sort of skill cutoff here somewhere around 10 days. There's certainly some other indications here that you could get some predictability beyond 10 days. You also see fairly good forecasts, not only of when events occur, but when events don't occur. And dynamical prediction is just important to understand when we're going to have quiet periods of extreme weather, not just when it does happen. So, after making this graph, it was pretty clear to us that, the predictability range is definitely going to be somewhere in this 8 to 12 day window if we're only relying on the individual members from GEFs and their environmental predictions that they can create. I guess I already had that on there. So here's 2017 just for reference. Not too much different. There are definitely a couple events look like there were better predictability. You also see some interesting things happening in the GEFS ensemble that looks like sometimes you get a run that becomes kind of very hot and stays sort of favorable in the long range. And that might have to do with something like, something happening to the model defaulting back to climatology, the model defaulting back to a base state that's not necessarily representative of any given run next to it. Which is something interesting that we've talked about for a long time, but really can't put our finger on at the moment. So if you're more interested, I'm going to jump ahead to something else right now, but the major graph for me for our paper was the Breyer skill score looking at tornado and hail. And you can see once you get to 0, you essentially have no skill versus a climatological forecast. And so for tornado, that's essentially sitting around, day 8, day 9, and for hail, day 11, day 12. That again, if you're only using dynamical prediction and you're focusing on a daily forecast. I want to be very clear here. This is just daily because some other work by John Allen, Mike Tippett, and Lepore have shown that you can actually get skill if you look at weekly aggregates, right? And you relax the forecast constraints, both in space and time. Let's look at the entire United States and let's look at weekly averages. We can get skill when we do that over climatology using things like CFS v2. But if we're looking at specific daily predictions, which is important in that convective forecast process, then at least using only our dynamical models, we're going to be kind of, we're at least stuck right now with the current version of GEFS at these thresholds of predictability. There's some other ways to visualize this using rock curves, and I'll leave you the paper that, but I do want to show a very quick case study, I'm a visual person, of how this might play out. So here's a day 15 forecast for 18 May of 2017. We have the probability, so we're using all the members, the probability of the supercell composite value being greater than or equal to 2. Sort of see this area highlighted in eastern Nebraska, northeast Kansas. We'll go to day 14, 13, and I'm just going to kind of let this play out. Day 12, 11, 10. So you see quite a bit of variability from run to run. By day 9, we see our first value of 60%, and that is kind of a value that I was keying in on initially in the paper and then ended up kind of dropping it because I didn't do enough analysis on the hindcast to see if that was a significant threshold for action. By day 8, the Storm Prediction Center has the ability to issue aerial outlines, both for 15 and 30% probability of severe weather within 25 miles of a point. And you can see in that particular forecast for 18 May 2017, the forecast from Storm Prediction Center had a predictability of too low. By day 7, the predictability stayed too low. The forecast values in the GFS supercell composite did go up as high as 90%, with agreement that severe weather would be seen over north central Oklahoma, at least based on the environment from GEFS. By day 6, the SPC issued their first aerial outlook for 18 May. Here's day 5, day 4, day 3, day 2, and day 1, just so you can see how that forecast, it actually ended up being a day 1 high risk across south central Kansas into western and northwestern Oklahoma. Here's how the forecast verified using the hindcast. You can see it was a fairly large moderate risk for hail, even very small area verifying of actually high risk, but a pretty large swath of moderate risk over that forecast areas too. So in other words, this might have been an opportunity to extend that sort of lead time at the operational scale. And certainly if we would have had, operational week 2 outlooks at this point, I think this would have been a great case for us as one of these sort of windows of what we call windows of opportunity. So here's some summary. And I think, if I had to just sum this up for you in a couple of sentences, if we're only using dynamical models for daily prediction, we're going to be stuck at the beginning of week 2 in our forecasts. And we need to really work on this area. This is the area of research that I want to just briefly touch on next, which is kind of dumping out wherever that skill line ends for the dynamical prediction and then making that jump over to the subseasonal forecast. So we've done a lot of work looking at some of these driving factors of climate variability, everything from the MJO to regional mountain torque, friction torque, atmospheric angular momentum, some of these other drivers that we think play a role in setting up how favorable the synoptic regime is across the United States for severe storms. One of them is the Madden-Julian oscillation. I'm not going to get too deep into this, but the Madden-Julian oscillation is just essentially trying to understand or assigning a value to where an anomalous area of convection is across the equatorial maritime region. So is the convection over the Indian Ocean? Has it propagated out towards the international date line? And we give phases based on this. And it's if you're not familiar too much with the MJO, it's not that important. But our goal was to kind of look at a case study and see and you'll see here in just a second, it's May of 2019, that the MJO does play really, it is the dominant mode of variability in the Northern Hemisphere, and its average orbit is actually right in that sweet spot of the subseasonal time frame that we want to be looking at, as is the GWO, which is the global wind oscillation, which looks at changes in atmospheric angular momentum. So this paper came out in GRL as well. This was May 2019. It was part of the subseasonal special issue that was put together by GRL. This is a pretty significant event. We had about 3 times the number of tornadoes during this 2-week period in May relative to the climatology. Obviously, May in the Central Plains is usually active for severe storms, unless you're talking about this year, which is another really cool subseasonal event, why a lot of severe weather didn't happen this year across the Central Plains. But it was also well forecasted, and I'll talk a little bit about that as well. But this is a pretty traditional MJO event that evolved, and one of the things that I really want to look forward to researching is do we have a catalog of these windows of opportunity, these forecasts of opportunity? Right now we don't, but we need a lot more work into understanding, is this sort of something that happens quite a bit? Is it something that only happens, when the stars align? How do we figure this out? Because this particular forecast was really good 4 weeks in advance. During this period, we had a 17 to 29 May, we had a deep trough in the west. Everything that you, as a convective forecaster, you'd be looking for, right? A nice long wave trough centered out the little Four Corners region, deep southwesterly flow over the plains, and significant low level moisture advection, setting up kind of a stationary dry line feature. And if I can get this to work, this is a radar loop during that 17 to 29 May period. And you can see the red boxes here are tornado watches issued by the Storm Prediction Center, and the yellow boxes are severe thunderstorm watches. And again, the date here is up in the upper left, but essentially this was just kind of daily barrages, very similar to the May 2003 event and others that we've had, at least that we know of, where the atmosphere day after day after day was very favorable for severe convective storms across the Central Plains. And that initial slide that I showed you with all the red polygons were all the tornado warnings for this period that were issued by the National Weather Service. So based on some previous research, looking at the global wind oscillation, and then again using the MJO, as you'll see here in a second, we wrote a paper in Monthly Weather Review that kind of looked at the changes in atmospheric angular momentum, and then kind of treated this almost as these phase space diagrams as a baseball or a softball player, right? And you see, if you've watched these games before on ESPN, they kind of have that strike zone, right? Where does the batter, where do you not want to throw the batter? It turns out if you like tornado outbreaks, you want low atmospheric angular momentum. So here's the y-axis. Everything down here is kind of lower than average. And you also want a decreasing time tendency. So you want to sort of be in this quadrant 3 where both AAM is negative and you have a decreasing tendency with respect to time. And the process here is such that we see MJO convection evolve, sort of a negative PNA pattern. This is usually found with increasing mountain and frictional torque. We see a rise in the budget of atmospheric angular momentum. And by the time this jet extends and retracts, it'll produce a trough in the western United States where an F2 tornado across the CONUS is about 15 times more likely than the climatological average. And so this is a very textbook, right, circulation that we would look for. But if you look at May 2019, 4 weeks prior to the severe weather outbreak across the plains, you did see a significant area of MJO convection that you can see it gets going here in phases 2 and 3. The gray circles here are the daily number of tornadoes as numbered down there in the bottom right. So here's 3 weeks, right? This convection propagated across the maritime continent. This is much more of like a phase 4, phase 5 MJO now. Again, circles corresponding to number of U.S. tornado activities, and these are the green here is the weekly MJO values. 2 weeks, this is getting out towards the date line, much closer to about an MJO 8-1. So there's, or 6-7, excuse me, the 8-1 transition will be coming up here. 1 week, we're definitely out right over the date line, if not just east of it. This, again, is OLR anomaly, so the green areas indicate where the significant or anomalous amount of convection is at. as measured by OLR. And then the week one of the event, sort of, you don't see a lot of MJO, you see actually a lot of suppression across the Indian Ocean. And this is where the tornado activity really begins to start. And then even reloads in week two. This transition from 7, 8 to 1 to 2 in MJO phase space sets up that, at least in this case, set up that West Coast trough, which synoptically favored severe convective storms across the Great Plains. So that was this, the fuchsia line here is that period 17 to 29 May 2019 with all the significant, or with all the tornado numbers by day shown there as circles. Here's how the synoptic composite evolved during that period as well too. We see sort of this jet extension beginning 3 weeks coming off of the Tibetan Plateau. The jet begins to extend a week in advance. Then you get this very nice wave breaking and regression of the pattern, retrograding of the pattern, and sort of reloading of this West Coast trough 2 weeks in a row, creating very adequate vertical wind shear across the Great Plains, and synoptically very favorable pattern for severe storms. So we've tried to harness this preliminary research into very informal extreme weather forecasts for tornadoes in the week 2 and week 3 timeframe. And in last month's edition of BAMS, you can read a little bit about that effort. The hindcast values that I was just mentioning will be out in the next issue of BAMS, I believe the June or July, the June issue of BAMS. That paper will be out. But this has been a really informal effort right now, and we're sort of having some difficulty, again, pushing this research forward. It's been, and I want to be careful what I say here, but it's been challenging because it's not necessarily weather and it's not necessarily climate, right? We're the subseasonal hot potato is sort of sitting in between these two. So there's been what appears to be some maybe agency discrepancies of who wants this in their ballpark and who wants to be in charge of these sort of research endeavors. We're not, to me, we're not even close to making, official forecasts, even for week 2, week 3, without doing some of this upfront preliminary research of just, what do these forecasts of opportunity look like? Can we blend things like machine learning and pattern regime prediction to understand where and when these synoptic environments are going to set up across the US. So I think, we need to do a much better job there, right? And get this sort of blue dot to connect to the orange in the subseasonal forecast window if we're really going to push forward weather forecasts in the week 2, week 3, week 4 timeframe for severe convective storms. So I've gone here just about a half an hour. And so as tradition with our PPAI panel, I'm going to shut up for a little bit, and I'd be happy to begin to answer any questions that you might have. Thank you so much for tuning in.
Thank you, Victor. So a reminder, if you have a question, use the raise your hand button that's next to your name, or if you have problems with your audio, you can also type your question into the chat box and I'll read out loud for you. All right, we have a question from John Nielsen Gammon. Go ahead, John.
Yeah, thank you. Thanks for the presentation, Victor. For the first part of it, for the forecast verification, you did everything in terms of a categorical forecast outlook, but you had to transform a continuous kernel density estimate for the observations and a continuous supercell parameter for the forecast to be considered looking at those things in terms of continuous variables.
That's a great question, John. And the answer is yes. I did not do that for the paper just for the ease of the categorical 2x2, right? But you could certainly imagine taking the probabilities both from the hindcast and the probabilities just from the raw supercell composite parameters, and perhaps doing a more comprehensive analysis. In other words, you could create Breyer skill scores, right, for each supercell composite value, or Breyer skill scores for each categorical threshold across the probability spectrum. But in terms of just ease of getting our results out there for interpretation, it was kind of easy just to say, let's take this one threshold of SCP and let's take this one threshold of our hindcast parameter and let's present that. One of the reasons that we chose, I didn't mention this, but one of the reasons we chose those specific values of PPH, the hindcast value, and the SCP is we just did a simple, cumulative density distribution to see, all right, what value of SCP corresponds right to this practically perfect threshold, and that's where we derive that value of 2 from the forecast as well. It actually varies by tornado and hail, but we kind of use 2 just to make it simple for the research. But yeah, that's a great question, and that's something that I think we're going to struggle with as we move forward with identifying extreme events out of these distributions, because we are talking, right, in this case, and in many cases when we're talking about PPAI of extreme events, we're talking about a very small sliver, right, of the statistical distribution, a very, very, these percentiles that you're looking at, the events that you're trying to extract are well into the 99.9 percentile most of the time, if not higher than that. So great question.
Yeah, and you can imagine that the actual probabilities might be different if you have 10 members predicting 3 versus 3 members predicting 10.
Exactly. And again, this comes with the struggle of, what's the optimum ensemble size? And these are all quite, is your ensemble under dispersed? And I'm eager to get my hands on the new GFS hindcast data once that come out. I'm hopeful, some of the preliminary things that I've seen show the skill to be quite impressive compared to the current version. I don't know how many more days that's going to translate to, right, in terms of predictability, but I think if anything, this hindcast data set is going to allow us to begin to answer that question of how common can we catalog these windows of let's call them windows of enhanced skill, or windows of opportunity to create skillful forecasts in those subseasonal to seasonal regimes. Yeah, I agree.
Thank you.
Thank you.
Any other questions for Victor? Let's see, one from Zoll. Go ahead.
Hey, Victor, nice presentation. I have one comment and 2 questions. My comment is about the sources of predictability on the S2S timescale. You mentioned the MGO and also the global wind oscillation. My recent work with my student, Doug Miller, showed recurrent weather patterns or weather regimes can also serve as a source of predictability on the subseasonal timescale. So using this concept on the hybrid model, we got skillful prediction. We are up to week 3, but what we examined is for weekly activity. That is my comment. My first question is, what challenges do numerical models have in addition to like model resolution or ensemble size to capture these kind of extreme events?
So let me take the first comment really quickly, because I just recently read Doug's paper in GRL, and I think it's fantastic, and that's why I'm stealing him to be my postdoc at Argonne. But I think he's done you guys did some fantastic work. I think that's one of the ways, right, to bridge this dynamical to statistical gap in using weather regimes and things like, random forests, machine learning, convolutional neural nets to identify, or self-organizing maps just to identify these regimes, and then, relax the forecast target to these, 5-day running means, windows, whatever they are, weekly running windows, forecasting for the month. I think the further you step back, the larger the signal is, in theory, the better predictability you'll have. And so I think that paper really opened my eyes to the ability to try to use those sort of methods in this work. So I can appreciate that. Regarding the comment on the ensemble size and what to do, predicting extremes at such small spatial and temporal scales like severe storms is going to be difficult given the environmental approach. And we know this. We know that even if an atmospheric environment is favorable on day 1 or day 2 lead time, there are seemingly environments that appear in the model forecast world to be relatively the same, although the forecast outcome is quite different. And so there are obviously sub-grid scale dynamics going on. We're not resolving, right, these events. And so I think there's some questions about, I'm really interested also in just advancing forecasts in the day 4 through 8 time window using very similar methods of passing in this coarse resolution data at that time frame and then downscaling it to a higher resolution, the resolution that we call CAM, right, the convective allowing model guidance, and then giving a forecaster 20 different outcomes at that day 4 through 8 window of perhaps what to expect. But at least for the foreseeable future, until models like the GFS ensemble and the European ensemble, are simulating out 15 to 20 days or 35 days with the, we'll have these weekly runs of the GFS that will go out 35 days. Until we get those to convective allowing and we get a huge ensemble, the forecaster, is going to remain relatively conservative in generating these aerial outlooks because they want to establish confidence. And I think that's one thing that I'm really excited about, again, about this GFS ensemble data set, is that we're going to have a pretty large ensemble, larger one than we have now. But we have that hindcast data set, right, where we can go back and say, here are the biases associated with these forecasts. They're well documented, and the researchers are able to go back and extract out and catalog these regimes, very similar to what was done in that GRL paper.
Okay, thank you. Could you give us some examples, like examples of useful products on the week 2, week 3 time scale? As you mentioned, when we relax our time scale for prediction, like moving from like a daily forecast to 5-day or weekly, it may seem we get some skills, but what we produce useful to users?
That is a question. That's an excellent question, and it's one that I think has to be done with forecasters in the room, right? And so I don't know if you can still see the screen that I'm sharing now, but I have kind of some spatial maps up of these types of forecasts. This is only looking at week 1 and week 2, where we have these sort of Chiclet style charts, which if you're looking at just this week coming up, it looks very active relative to climatology. These are the sum of the supercell composite parameter, very similar to what we were predicting in the paper. But I mean, creating like, super ensembles of these chiclets, I think is important. And then perhaps displaying the information spatially so that forecasters, you could essentially create, using machine learning and the environmental information, you could easily create a first guess severe weather outlook for both week 1, week 2, week 3. Of course, the SPC forecasters want it at the daily scale, but depending on the user, there's no reason this information couldn't be aggregated and sort of create severe weather forecasts at these lead times, giving very similar methods that are already being used at the day 1, day 2, day 3 timescales. So I'm a big fan of these chiclets. I think they're a way for a forecaster to very quickly look at them and gauge understanding of ensemble spread. Really just capturing the forecast in one image. I think they're really effective tools, in my opinion.
Yeah, it contains a lot of information. Thank you.
It does, and it requires training, and I think more importantly, it requires giving the forecasters, what they're most comfortable using. But I think they're definitely a way forward, especially when combined with the spatial maps, where the forecasters can go in and then tweak them based on experience, or based on specific weighting schemes. Maybe they want to weight the European 40%. They can adjust these things based on other methods. But I'm really looking forward to the day where we have week 2 and week 3 outlook that are in experimental phase, that are using some of these types of methods. But in my opinion, we have a long way to go because we have a lot of research still to do. So
Other questions?
Thank you.
Yep. Other questions? We would like to also hear from non-panel members as well. Let's see, I don't see any movement on here or in the chat boxes yet. All right, I guess if we don't have any other questions, we could end the PPAI Panel Webinar series early today. Give you a couple more seconds unless anyone has any last minute.
Yeah, so for those of you who follow me on Twitter and understand the frustration here is that it's hard to get over that. I mentioned this subseasonal hot potato, this hurdle that we've been struggling with of trying to find out whose lane this type of research is in. When we're talking specifically about predictability, it seems that NOAA should be involved at some level. However, I can understand the non-willingness for NOAA to get involved, given that their basic research hasn't been done yet, and is still in some ways at a very theoretical and applied level. So this is one of the reasons for me joining the CLIBAR PPAI in the first place, is to begin to talk about some of these issues where we can make coordinated efforts to advance our really, at the end of the day, our skill in forecasting these extreme weather events for society. So I don't know if anybody has thoughts on that. Maybe I'm just getting jaded in my attempts for funding, which is a struggle. But yeah, it's an issue, but I think we can do a lot. We just need some investment. And that's true for a lot of the talks that I've seen so far.
Hi, this is Andy. I guess I could weigh in a little bit on that. And first, I just want to say, very interesting talk. I started late, but I feel like the way you're looking at these things is really excellent. But on this topic of funding, I've seen the same thing for a long time, where predictability is kind of a minor science question to some extent, or has been, within agencies that fund science, National Science Foundation. And as you get over to NOAA and NASA, which is becoming increasingly applied, you see a lot more funding on the prediction side or forecasting. But being within NCAR and also having funding from a variety of groups, NOAA, Reclamation, Corps of Engineers, DOE, I feel like there's, as you get toward this forecasting area within an NCAR type place, there's a certain nervousness about it not being scientific. And I think it gets back to this idea that predictability and prediction is kind of it's almost like an engineering minded end of the science world. And so as a result, I feel like there is a gap between, if you think about it in terms of research levels that are being funded, like the whole TRL or RLs that NASA and other agencies use now. You see things funded down at the sort of 1-2 level in the science end, which end up being things like model development. Whereas you see things starting at the 5, 6, 7 level funded through the operational agencies, including NOAA, leaving this gap that's down where it seems like you want to work, which is this 3-4, you're kind of developing ideas that could be useful in a forecasting system, but you're not quite sure if there's predictability there. And ultimately, I think the answer comes in recognizing that predictability, Earth system predictability, is sort of a subsection of science that's worthy of recognition almost in its own right, versus just sort of climate variability, climate, long-term trends and evolution and things like that. So I definitely perceive some of the same things that you've mentioned.
Thank you. I agree, and it's definitely a struggle when you're trying to push it forward, and we still have questions about the predictability and just basic science questions about things like atmospheric angular momentum and the theoretical role that it plays, right, in the Earth system variability, and how much of the MJO accounts for changes in AAM, and the role of frictional torque and mountain torque. These are unanswered, very basic theoretical science questions that can be tested not only observationally but through theoretical, the use of climate models. And I know I showed a lot here that was very applied in nature, given really focusing on the predictability, but there are just some basic standard outstanding research questions, I think, that also need to be tackled too. That's probably why it makes it a little bit extra frustrating in this case. But yeah, I hear you loud and clear, Andy.
Yeah, thanks for bringing it up.
Anyone else have questions or comments? All right, Victor, do you have any last remarks before we close this then?
No, other than thank you for tuning in. I know I don't know how many of us are states are still in lockdown, but we're still playing it safe up here with COVID. So I appreciate everybody tuning in. And if you have any other questions that you don't feel comfortable asking now in public, please, my email's right there. Feel free to shoot me an email, and I'd be happy to correspond and work with you. But looking forward to next week, right, for the PPAI summer meeting.
Correct. Next week, Monday to Wednesday. All right. So yeah, and I do also want to thank you too, Victor, for your presentation. We appreciate the time you took in preparing this talk, and we are really looking forward to your contributions to the panel. So for everyone else, a recording of this webinar will be on our YouTube channel this week or next. I'll try my best to put it out before the panel meeting, and I will share this link once it's uploaded. You can find this on the US Collaborator website, but also on our Twitter account pretty easily. So we will take a short break from the webinar series, and we'll reconvene in 2 months with our next PPAI panel webinar that's tentatively scheduled for September 16th. So thank you everyone for joining, and have a great day.